Welcome to the March edition of the Guildford Astronomical Society. And today our sort of speaker is Clare Burridge from the University of Nottingham, Professor of Physics there. He's going to talk to us about cosmology, dark energy from cosmology to the lab to the laboratory, which I'm looking forward to as a former cosmologist. And then after the break, Jonathan is going to tell us, if you remember, he started up a exoplanet interest group, and we had the first meeting of that. So he's going to just give a quick report of that, and just to remind people, and also if anybody's interested, please they can join. Julia is going to do what's up, and Tim, I forgot to put it on the slide, but Tim's going to have a quick discussion about the observing session this weekend. And then if there's anybody wants to discuss, we can discuss anything after that. So with that, I'll pass over to Clare, who's been very kindly waiting. We got in at 7 o'clock so we could test all the equipment, and it worked first time, unusually. So she's been very patiently waiting to meet you all.
That's okay. Thanks very much for having me. And I should say at the start that I'm really sorry to do this virtually and not to be there with you in person. I was hoping when I agreed to come talk that I could come down, but unfortunately things at work meant that I'm stuck in Nottingham this week and wasn't able to come and see you. Right, let me share my screen so that you can see my slides. Okay. Somebody just tell me that that's working okay. I'm going to guess that everything that you can hear me and that you can see the slides okay, but please shout if that's not the case. Okay, so what I'm going to talk about is dark energy, and if you don't know what that is, that's fine. We're going to go through that and how we know that it's there in our universe. And I'm going to tell you a little bit about how we can learn about this fundamental mystery in cosmology by doing experiments in the lab. So really connecting the very largest scales in the universe with some of the very smallest scales that we can study. So roughly what I'm going to talk about in the next kind of 45-50 minutes is here. So we're going to talk first of all about how do we know that we need dark energy. And to do that, we're going to ask two much more basic questions about the things that we can see in the sky. So if we look up at the sky and we can see that there is another galaxy out there, how do we know how far away it is? And can we tell whether it's moving? Is it moving towards us or away from us? And if so, how fast is it doing that? Then we're going to put those two pieces together and we're going to see why that tells us that we need this extra mystery component in our universe, which is what we call dark energy. And then the second part of the talk is going to be about how we study it, and more specifically about the things that I've been doing. So hopefully that sounds okay. So yeah, so the first question we're going to ask is, how do we know how far away a galaxy is? And as you know, as astronomers, we can't just take our measuring tape, hold one end, in the lab, and take the other end to the distant galaxy and figure out how far away they are. All we have got is really the light that is coming to us from that distant galaxy. Well, now we've got gravitational waves as well, but for the moment we're focusing on the light that comes to us from those galaxies. And so what we would like to have to try and find out how far away things are is a standard candle. So something that burns with the same brightness everywhere in the universe. And that's, I think, relatively easy to understand, that things that are closer to us look brighter, and if you move them further away, then they're going to look dimmer. So the mathematics behind that is known as the inverse square law, and that's basically just the idea that if you've got a source of fixed brightness, the light from that gets spread out over a sphere, and the further away you go, the bigger that sphere gets, the light gets spread out over a larger area. And so what we see here on Earth is less light. So that's something we can predict. So if we knew how bright an object was, and we could see how bright or dim it looks in the sky, then we could figure out how far away it is. But of course, the challenge there is knowing how bright your object was to begin with. If we're sat here on Earth looking out at the sky and we see one object that's brighter and one object that's dimmer, how do we know that the brighter object is brighter because it's closer to us and the dimmer object is dimmer because it's further away, and not just one is shining more brightly than the other to begin with, giving off more light? So we're extremely lucky that the universe, or that physics has given us an object that actually does have this property that it burns, it gives off the same amount of light wherever and whenever it happens in the universe. And that's a type 1a supernova. So these are explosions of stars that happen in a very particular way. So what happens is that you've got a white dwarf in a binary system. So it's got a partner, they're orbiting one another quite happily. But our white dwarf star is sort of slowly stealing material from its neighbor in this binary system. And as it does that, it's getting more massive because it's stealing all this extra material. And the simple way that we can understand how stars burn is that they're a balance between, they're balls of gas, and they're always a balance between gravity pulling stuff in towards the center, gravity pulls in, and the thermal pressure of all the stuff burning in the star pushing out. And if a star is stable and long-lived, you have a nice balance between those two forces. So the gravitational force pulling stuff in is balanced by the thermal force pushing stuff out, the thermal pressure pushing stuff out. Now, as our white dwarf star is kind of stealing all this extra material from its neighbor in the binary system, it destabilizes that balance. So you've got more material, so gravity's got more stuff to pull on, but you don't have as much stuff. There's no compensation in the kind of heat, the pressure pushing stuff out from the star. So what you get is a collapse. So everything in the star collapses down to the center. You get a massive thermonuclear explosion, and everything kind of gets pushed out again and a lot of that gets turned into light. And what is interesting for us is that always happens at pretty much the same mass. So as the white dwarf gets, it's stealing all this extra material, as its mass gets to about 1.4 times the mass of the sun, that's the point at which it becomes unstable. And then you get this massive explosion, and through the fact that we know that we can convert mass into energy, energy into mass, that's E equals mc squared, when that explosion happens, all of that 1.4 solar masses, or a lot of that 1.4 solar masses, gets turned into light, and that gets emitted out, and that is so bright that we stand a good chance of seeing it. So this on the slide down here is two images of the Pinwheel galaxy, and you can see on the left there's an arrow pointing at a relatively unexciting spot on one of the outermost spiral arms, and then on the right hand side an arrow pointing at a really bright spot. And these images obviously not quite identical, they weren't taken at the same time, but that arrow is pointing at the same spot in the galaxy. And you can see that in the right-hand image, there's a bright spot that isn't there in the left-hand image. And that's one star, our one white dwarf, exploding on top of the background of all of the other stars in the galaxy that we can see. Okay, so now we've got these objects that we know always give off the same amount of light, 1.4 times the mass of the sun's worth of light. So now we can start to say the ones that we see that are brighter are closer to us, and the ones that are dimmer are further away. So the other thing that we said we were going to try and figure out is whether the galaxies are moving, and if they are moving, you know, are they moving towards us? Are they moving away from us? And how fast are they doing that? And again, this is something that we have to do indirectly as cosmologists, as astronomers, because we can't go out into space and just kind of measure the speed. We have to do it from here on Earth. So what we use here is the fact that if the source is moving, then the light that's coming to us from that source, which is a wave, gets stretched or squished, depending on whether the source is moving away or whether it's moving towards us. Now, because the wavelength of light is connected to its color, if the light is getting stretched, the wavelengths are getting longer, and we're going to see a redder light. And if the source is moving towards us, the wavelengths are getting squished, they're getting shorter, we're going to see a bluer light. So this is exactly the same effect as the Doppler effect that you might know for sound. So why the pitch of a siren changes as it's coming towards you and going away. This is exactly the same effect here, just with color instead of pitch for the sound. But again, we have the problem that to use this effect, we have to know what the color of the light is to start with. Is a star or a galaxy that we can see on the sky looking redder because it's moving away from us? Or is it just that it's burning stuff that's giving off more red light to start with? So the extra piece of information we need is to think about the full spectrum. So on the left here, this is an image of a spectrum from the sun all the way in the visible wavelengths, from the red end of the spectrum down to the purple. And you can see this quite distinctive pattern of black lines across this. So these are absorption spectra. And what that means is that if you've got any gas, any particles in between the sun and us, they have particular colors of light that they like to absorb. So different elements have different favorite colors. That's all to do with their quantum structure. And so you get these very, very sharp, distinctive lines where where you don't see any light because it's all been absorbed by all of the particles between the sun and us. So it's a pattern you can predict if you know the behavior of those elements. And so you can go and look for it in the data that you take from from any other object in the universe. And so what we can see, this on the right-hand side now, is a spectrum from a supercluster, so from another object. And we can see the same distinctive pattern, but now with all of the lines shifted up. Okay. And that, at least how we think we should understand that is not that all of the different elements, so oxygen or iron or sodium, have different favorite colors in different parts of the universe. Instead, what is happening here is that this supercluster of galaxies is moving away from us. And so as it's doing that, the light is getting stretched. The light that's traveling from it to us is getting stretched. And those lines move, all of the light that we see is getting shifted towards the red end of the spectrum. And as that happens, those lines get shifted as well. So if you can measure that pattern of lines and compare it to what we see from the sun, then you can work out how fast other objects in the universe are moving away from us. Okay, so why did we want to know those two things, how far away a galaxy is and how fast it's moving? So we want to use those two things to test our theory, first of all, to test our theory of general relativity, because what that theory tells us is that those two things should be related. So I'm not going to go through the maths of this at all, but this is just to show you that there is a lot of maths underlying all of this, and we can make really nice predictions with it. But really what is happening here is that space and time can mix together. And the space-time tells matter how to move. So you can have curvature in your space-time that tells things how they should move and evolve. And the matter tells the space-time how to curve. So these two things are endlessly talking to one another. This is our theory of gravity, that matter is telling space-time how to curve, and then on that curved sheet, other matter will roll around. And what that means for our cosmology is how the universe evolves depends on what it's made of. So what things we put into our universe affects how it changes and how it evolves. So we put those two measurements that we can make, how far away galaxies are and how fast they're moving, together on a plot. So this is an old plot. This is from over 20 years ago. I'll show you a more modern version in a second. But what is, although it's got slightly different names, what is on these axes are what we've been talking about. So on the vertical axis, this observed magnitude, that's the brightness of our supernova. So that's how far away the galaxies are. And on the horizontal axis, that's the redshift. So how much the light gets shifted into the red. That tells us how fast the galaxies are moving away from us. And this plot shows a bunch of information from lots of measurements of different supernovae. And first of all, we can see that our everything is lying very nicely on a line. So this bigger image is a zoom in on this blue-red part of the bigger plot here. And you can see everything is lying nicely on a line. So first of all, our theory of gravity is working. It told us that these two quantities should be related to one another, and they are. But then we look a little bit more closely, and you can see that in this plot, half of it's been colored blue and half of it's been colored red. And what that is telling you is where the data would be saying the expansion of the universe is accelerating, or where it would be telling you that the expansion of the universe is decelerating. Now, the standard story to give you the history of the universe in a couple of sentences, what we think has happened is that at the very beginning, there was a big bang. There was an explosion that sent everything flying apart. And then time goes on, the universe evolves. And so all of that stuff that was initially moving apart from one another, well, it's attracted to everything else through gravity. And as we said, gravity just pulls stuff together. So at some point, you would expect things to stop moving apart and maybe start to come back together. So so maybe you would have expected the expansion of things to stop, or at least to start to slow down. So that would be a decelerating universe. And when people went out to measure these observations of supernova, that is very much what they were expecting to see. Okay, that was the standard story. Everybody's expectation was that the data would lie somewhere in this red region. And maybe what you can see or convince yourself by eye is that actually that's not what the data are telling you. That actually slightly more of these points on this plot are lying in the blue region compared to the red region. And so this is one of the very first pieces of evidence that not only is the expansion of our universe not slowing down, it's actually starting to speed up. So this is a more recent version of the same plot. I think there's now order 800 supernova observations here. You can see again, everything still lies really, really nicely on this line, relating how bright our supernova are to how red the light from them is looking. And again, maybe you can convince yourself that there's a slight upward curve to this line. And that is the evidence that we have that the expansion of the universe is accelerating. Now, actually, when we put this together with the other observations that we have in cosmology, it tells us that the universe actually needs two extra components that we call dark matter and dark energy. Now, dark matter is what we need to explain the rotation of galaxies. And dark energy is what we need to explain the expansion of space in between galaxies, if you like. And excuse me. What we can see is from putting all of the data together that the ordinary matter, so everything we are made of, everything the planet is made of, everything the stars that we can see are made of, that they make up about 5% of the matter in the universe today. Another roughly 27% is made of this dark matter that lives in the galaxies, and then about 68% is the dark energy. So whatever is driving the accelerated expansion of the universe. So it's a big deal. It's a lot of our universe today, and we don't know what it is. So that's that's what I'm focusing on for the rest of the talk. So I say we don't know what it is. Actually, initially, this looked quite straightforward to explain. So we said that gravity likes to pull things together, and that's why we expected the expansion of the universe to be slowing down instead of speeding up. But actually, there is an extra term that we can add into the Einstein equations. And again, I'm not going to go through the maths, but this is just a point. This is a term that you can or can choose not to have in these equations. And there's been a bit of a debate about whether it should be there or not. But if it's there, it can cause the expansion of the universe to accelerate. So perfect, job done. What was all the fuss about? All we need to do is go out and measure how fast the universe is accelerating. That tells us the value of this constant, and we're done. Okay. The reason that's not the end of the talk is because gravity isn't the only thing that we have to worry about in cosmology. So if the universe was just gravity, everything would be fine. We'd just pick a value for that constant and we'd be done. But the other thing we have to worry about in cosmology and fundamental physics is quantum mechanics. And quantum mechanics is weird in the sense that everything's a bit uncertain. You can't just say a particle is here or moving at this point, moving with this velocity. There's always an uncertainty on that. That's Heisenberg's uncertainty principle, if you've come across that before. And so this is a sort of sketch of that in the way that we are used to experiencing the world. If you put a ball in a bowl and you leave it long enough, it happily sits at the bottom of the bowl and it doesn't move and it doesn't do anything. In a quantum theory, if you could zoom in far enough to see, the ball wouldn't just sit at the bottom of the bowl. There would always be some jitteriness. The particle always has some energy. You don't know, you can never like pin it down at one particular point in space. And maybe you can believe that jitteriness, the fact that these particles are always kind of moving, you're never quite sure where they are, has some energy to it. And that energy, this jitteriness of the particles is there even in empty space. So in empty space, there's always the possibility, even though you thought your space was empty, that a particle could pop in and out of existence for a brief period of time. And again, that jitteriness, that uncertainty about whether particles are there or not, gives us an extra bit of energy. So, and it turns out that energy has the same behavior, is exactly what we wanted. It's something, because it's the same at all points in space and all points in time, it turns out to behave exactly like our cosmological constant that we added to these equations on the previous slide. So actually, maybe this is even better. Maybe it's not just that there's a constant in our theory that we need to fix and everything is fine. Maybe we can make a prediction for the value of that constant. We know what our theory of quantum mechanics is. We just do all the calculations for what this energy is in the vacuum, make a prediction. If that matches observations, everything is good. The problem is that you can make that prediction and you get the answer massively, massively wrong. So the prediction from quantum mechanics of what the cosmological constant is, so how fast the expansion of our universe should be accelerating, is wrong by 120 orders of magnitude. So that's possibly the worst prediction anybody's ever made. And so that's really the big mystery here, is how are our theories predicting something that is so far away from what we see when we look out at the universe. Just to give you a sense, if the universe was expanding as fast or accelerating as fast as our quantum theories predict, there wouldn't even have been time to form galaxies and stars. Everything would have just got ripped apart immediately, like almost immediately. Like the expansion would have become so rapid so quickly. So This is definitely not the universe that we live in. So we can break this down and ask, well, why don't we see this enormous cosmological constant? Why don't we see this enormous acceleration? But then physicists are like, okay, well, maybe something sets it to zero. That's always the first answer. Okay, we got this wrong, so there must be a reason it's actually zero. But that doesn't match our observations either, because what we're seeing is not no acceleration, we see some acceleration. So if it's not enormous, but it's also not zero, how do we get to that point? And the other thing that is weird here is, why is it that this small value, so not enormous, not zero, why is the small value chosen exactly so that the cosmological constant dominates today? So this is an overview of the history of the universe in this slide. So the age of the universe on the horizontal axis. So we live over here on the right-hand side. The beginnings of the universe of the Big Bang are over here on the left. And on the vertical axis is density of stuff. And as you probably know, in the early universe, everything was very hot, everything was very dense. Universe expands, things cool down, things get spread out a bit more, things become less dense. So the blue line, if we just look at that for the moment, that's the amount of matter. So when the density, when this line is high, that means matter is all packed together. And as it falls, as the universe expands and the universe gets older, that's the universe expanding, the stuff getting spread out over bigger distances. And we can predict how this falls off, and it matches what we see very well. What is the green line is this cosmological constant term. So it's a constant, it doesn't change as the universe gets older or bigger. And it turns out that that has come, if it is a constant, to dominate the universe just before we're here to see. So roughly around the time of the formation of the solar system, that becomes the most dominant component in the universe. But how on earth, if that's the right answer, did we end up with a universe that chose as its initial, right at the beginning, to have loads and loads and loads of matter in it, very, very little of this cosmological constant, so that as the universe runs forwards, just at the point where these two things become of the same magnitude, we are here to see that. That feels very, very unnatural, and against all of the principles that we know of in physics and astronomy, where we're not supposed to live at a special point, right? We don't live at the center of the solar system, we don't live at the center of the galaxy, and we shouldn't really, if our understanding of physics is right, we shouldn't live at a special point in time either. So there's something very weird about the fact that this is happening. Okay. So this is when I'm going to switch gears. So everything I've told you so far is sort of the standard story in cosmology. You could have had any cosmologist come and give you a talk about dark energy, and they would have told you sort of a similar story about how we know that the expansion of the universe is accelerating, and what that means for what our universe is made of, and why that's weird. What I'm going to go on to talk about now for the next kind of 15-20 minutes is, well, what is dark energy? What could it be? And how do we go about testing that? So the sort of general the thought process here is that we don't understand the expansion of the universe. We don't understand why it's accelerating in the way that we can see that it is. So we need to add in something new. And dark energy is really the catch-all name for the something new that we add into our universe to try and explain this accelerated expansion. Now, there are lots of people with lots of different ideas about what that might be. And there's no consensus yet in the community about whether one of those is more or less right than the other. So we're trying to have good ideas and we're trying to test them, but there isn't one definite, like, this is the answer, or this is even the most likely answer at the moment. However, one thing that's a common consequence of all of these theories, or a lot of these theories that people are coming up with, is that whatever it is that you introduce to be your dark energy, it brings a new force into your theory of physics. So normally we talk about, we've got gravity, we've got electricity and magnetism, and we've got the strong and the weak forces. Those are the fundamental forces that we teach our students about. So this would be an extra force in addition to those that's related to our theory of dark energy. And now, if that's quite a common prediction of these theories of dark energy, maybe we can go and look for the force. And if we can find it, that's great. That's evidence that we're thinking along the right lines. And if we don't find it, then that tells us that a lot of these theories that try and explain what the cosmology is doing by introducing this extra force are wrong. Okay. So that's really where my research has been focusing. Because the problem is that we haven't seen any extra forces. We've been looking for forces and measuring very carefully the motion of objects for a long time. This is obviously an old image of the motion of planets and a comet here in the solar system. We can track their motion very, very carefully, and it's really, really well explained by gravity, Newtonian gravity, Einstein's gravity, as we get closer in towards the sun. There's no scope there for adding in an extra force. Or at the very least, if it is, it has to be incredibly tiny. We also haven't seen any extra forces in the lab. So this is an image of an old experiment due to Cavendish that was done in Cambridge, to try and measure gravitational forces between these large objects, so the large circles at the bottom here, and these little tiny test particles here. And basically what this is looking for is to see the attraction between the little objects and the big ones. So Cavendish used this to test the theory of gravity, and people have been doing similar versions of this experiment, more and more, ever more precise versions of this experiment in the lab. And again, no evidence of any extra forces. So this feels like it ought to be telling us that our theories of dark energy are wrong. So if our theories of dark energy say there are extra forces and we haven't seen those extra forces, then it, you know, that should be telling us that we're missing something. Now, to understand what it is that we might be missing, I want to think a little bit about how we transmit forces. Now, forces each force has a particle that is carrying the force, is transmitting the force, sending the information. For light, so for electromagnetic forces, that particle that's carrying the force is the photon. For gravity, it's hypothesized to be a graviton, which we haven't actually seen yet. And for the weak and the strong forces, we know, again, the particles that transmit those forces. And just as our person on the slide trying to throw a tennis ball and a dumbbell, the heavier something is, the harder it is to send it over long distances. So if our particle that's transmitting the force is light, like our tennis ball, you can throw it a long way, and our light particle can transmit forces over longer distances. If our particle is heavier, like the dumbbell, you can't throw it as far, so it can only transmit the force over quite a short distance range. So maybe that's the answer for us. Maybe we haven't seen our force yet because it's really, really heavy. It doesn't actually transmit information over very long distance scales. It's been hiding from all of our experiments because it's just too short range. The problem with that is if it needs to hide from our laboratory experiments, which let's say we're doing on distances of a millimeter or sub-millimeter scales, and it hides from our measurements in the solar system, how on earth, if it's that short range, could it be doing anything interesting for our universe on the very largest scales? So that's not quite the answer, making the particles heavy. What some of these theories can do, and what I think is really interesting, is that actually for some of these theories, the mass of the particles can change. And it changes depending on the environment, on the density of the environment. So in the vacuum of interstellar space or intergalactic space, the particle becomes very light. Becomes like our tennis ball. We can use it to transmit forces over very long distances. So it can be relevant on cosmological scales. It can be doing something interesting for our cosmology. But in a dense region, and that's sort of what I'm trying to illustrate on this side. So this is like lots of material packed together. Our particle transmitting our force becomes much heavier. We can only send the information over shorter distances. And we can't see it so well. And these particles, if they exist, and if they do this, get called chameleons. So they're called chameleons because they change their behavior, change their mass, depending on the environment, to try and camouflage themselves from our experiment. So a little bit like chameleons are supposed to be able to camouflage themselves depending on their surroundings by changing color. Our chameleon particles change their mass. And if they become heavy in our experiments, then we don't see them. They're camouflaged, they're screened from our view. So that's then what we want to try and go and look for. Can we see, is there a way of trying to see this particle that's trying its best to camouflage itself from view? Now, one of the things that we can do is actually a test that we have been doing for a long time, which is to ask the question, do all objects fall at the same rate under gravity? Now, going way back in time, people might have thought that a larger or a heavier object would fall faster. And then Galileo came along and he did some very nice, very precise experiments, unfortunately not dropping things off the Leaning Tower of Pisa, but he was able to prove that actually all things fall at the same way. It doesn't matter how large or how heavy your objects are, they all fall in the same way under gravity. And what these theories, these chameleon theories, are suggesting is actually the opposite of Galileo and the opposite of the old idea, that if you've got a sufficiently small object, it's so small that our chameleon particle doesn't have enough room to do its clever camouflaging behavior, and so the small object does feel this extra force, whereas the large object, which is big enough for the chameleon, for this extra force, to change, because this is a dense environment inside our object, this one doesn't feel the extra force. So both of these objects are feeling our gravity, but the small one feels the extra force, and so it falls faster. So that now is an idea that we can go and test. Very quickly, I'm just going to say you can do this with astronomy, going back and looking at galaxies, because what we're trying to do is we're trying to look to see whether large objects and small objects fall in the same way under a gravitational force. This is a very simplistic picture of a galaxy, but basically what this is saying is that we've got lots of dark matter in a circular halo, and then gas and stars in a disk in the middle. And it's possible that gas and stars gas is made of small objects, stars are large objects. So maybe if you've got a small galaxy made of gas and stars falling towards a much larger cluster of galaxies nearby, you might see a difference between where the gas is and where the stars are, because the gas is feeling this extra force. And that is something some of my colleagues have gone away and tried to look for in their data. But what I'm going to talk about, and what I have been working on, is whether we can test this in the lab. So now we're not just dropping small and large objects off the Leaning Tower of Pisa, we're dropping objects that they're so small that we're dropping atoms. So we're asking, if we let atoms fall, do they fall in the same way as other bigger objects? And we're lucky that we started thinking about this at a time when our experimental colleagues were developing, for other reasons, ways of measuring how atoms fall. What acceleration do they experience? So that's a technique called atom interferometry. But it basically just means that you have a very, very fancy piece of kit. So there's lots of laser optics here, lots of cooling and trapping of your atoms. You put them into the center of this vacuum chamber. This is a picture of an experiment that our colleagues did at Imperial College. You let the atoms fall, and you can measure extremely precisely the forces they experience. And so they have done, so colleagues in London at Imperial and at Berkeley in California have done these experiments to look to see if they can see these chameleon forces, and they haven't seen anything. And so they're able to say that if there is any acceleration on these particles due to dark energy, that force is smaller than 200 nanometers per second squared. That means it's 10 million times weaker than gravity if this force exists in the experiment. So what does that mean for our theory? So this is, to sort of show you the impact of this, this is a sketch of the parameter space of this model. What that means is that there's a parameter, there's a number in the theory that we don't know from the start, that controls how strongly in intergalactic space the force would interact with matter. If the force is as weak as gravity, we'd be living over on the right-hand side of this slide. If the force is as strong as the nuclear forces, we'd be living over on the left. And when I started working on these theories, all of these options were open. And that's 10 to the 18 orders of magnitude, so a factor of 1 million trillion that we didn't know that this kind of number could vary between. Now, then there were a few constraints put on the model. So it turns out that for these really, really strongly interacting particles, strongly interacting theories, that you can get constraints from particle colliders like the LHC. And that for the really, really weak ones, where the force is as weak as gravity, you get constraints from those Cavendish type experiments looking for gravitational forces between objects in your lab. So there were some constraints that took us down to 10 to the 14 orders of magnitude, or a factor of 100 trillion. So, okay, better than nothing, but still a huge amount of open theory space that we didn't know what to do with, or where the right answer was supposed to be. And what our experiments with the atoms, the ones that I showed you the photograph of on the previous slide, what that has been able to reduce this down to, so it's been able to rule out all of this blue region. So we've got this little window left where our theory could be, so 1 order of magnitude, about a factor of 10. So the theory isn't ruled out yet, but this is we've made a huge amount of progress already in the last kind of 5 to 10 years. And this little window we know can be covered with a next generation experiment. And actually colleagues at Imperial are working on that at the moment. So there's a chance that our theory was right, that this is the right way to explain dark energy. And we are about to, with the next generation experiment, discover that the theory is living in this little window here. Or we do that experiment as well. We don't see anything, in which case we would say this theory, you know, we looked for it, it's not there. And everybody trying to come up with theories of dark energy had better go back to the drawing board and come up with a different way of explaining why the expansion of the universe is accelerating. Okay, just before I end, just wanted to zoom out a little bit and put this back into context of what other researchers are doing, because this is certainly not the only way you can try and learn about dark energy. And this is a really exciting time because last summer the Euclid satellite was launched. Its mission is to go and study dark energy and dark matter in our universe and try and test our theories and figure out what's going on. So it was launched on a SpaceX rocket last July, and it is traveling, or has traveled, an awful long way away from the Earth and the Sun, but it's happily sat in its orbit now, and we've already by the end of July, we got first light images from the instruments, and everything is working really, really well. So lots of exciting cosmology to come from Euclid over the next few years. And I think I'll skip that. So just to summarize everything that I've tried to talk about today, we know that the expansion of the universe is accelerating. That's really kind of an established fact about cosmology now, but we don't understand why. Dark energy is the name that we give to whatever the substance is that is causing this acceleration, and we don't know what that is. We don't really know any of its properties. But many of the theories that we have predict this new chameleon-like force that can change its behavior depending on the environment, and both hide itself from our conventional ways of looking for new forces, but also gives us new opportunities to try and detect it with dedicated experiments. So it's really an exciting time for the study of dark energy, both with all of these new laboratory experiments and also, as I said, with Euclid and the new space-based observations that are going to come in the next few years. Okay, thank you very much.
Thank you very much, Claire. Any questions for Claire?
Were we able to resolve the Hubble tension or explain it? Would that get us any closer to actually having a theory for dark energy?
Okay, very good. So just in case there's anybody here who doesn't know what the Hubble tension is, so that is the fact that different ways of measuring the Hubble constant, which is the rate at which things are currently expanding, or the size of our universe currently, give us different answers, and answers that don't overlap within the precision of the measurements. So it's a bit of a problem for cosmology at the moment. Still kind of an ongoing debate about whether we really understand the measurements well enough to be confident that there is a tension here, or whether there's really, it tells us that there's something missing from our cosmological picture. So to answer your question, it seems like what the Hubble tension is telling us is that we are missing something about what is happening in the early universe. So most current ways that people try to address that problem focus on changing something in the early universe. So it's not immediately obvious that that connects to our theory of dark energy at quite late times and what the universe is doing now. However, one of the things that people suggest is that maybe there was an earlier period of rapid of accelerated expansion as well, and that might fix the Hubble tension. And if that turns out to be the right answer, then I think that is suggesting, okay, maybe the universe actually goes through regular periods of accelerated expansion. Where we're living now is not that special. Maybe there were lots of periods like this that happened and will happen in the future. And that certainly would help us in understanding kind of what kinds of things the universe does, what's unusual, what's usual, and to help us start joining the dots between these things.
Thank you. Anybody else got any questions? Tony. Hold on. Do you want me to hear you otherwise?
68 point something% is presumably the mass equivalent.
Yes.
Is that correct?
Yeah.
So where what we can experience is 4.8 or something %.
Yeah. Yeah. So it's
Does,
no, go on. Sorry.
does that mass have the same sort of gravitational effect as other mass? And why doesn't the mass in dark energy cause an attraction because of the gravitational effect?
Yeah, very good question. So it's because it has other properties than just having mass. So if you like, when we talked about the stars early at the beginning of my talk, and we said they are a balance between gravity pulling stuff in and the thermal pressure pushing stuff out. So the mass of the gas in the star has the property both that it has mass, but also that it has temperature, and that is an outward pressure. And what this dark energy substance has to do is, yes, it has mass, and that would want to make things clump, but it has pressure pushing things out as well. But it has way more kind of outward pressure making things expand than anything that we know of on Earth. So it does have mass, and there is that force trying to pull things in, but it also has this counterbalancing, or not just counterbalancing, but overwhelming outward pressure to it as well, which is what causes things to expand.
I'll be back in a second. This is my exercise for the day.
Why would you expect the mass or gravity to cause the universe to contract or slow down? I'm thinking that if the universe is the same in every direction, if you take a lump of mass, it's being attracted equally on average in all directions. So there's no net force causing it to move as such. I can't see why gravity would cause the universe to collapse or slow down.
Yeah, so if things were completely evenly distributed, you're exactly right that the forces would balance exactly. So if we had a perfectly regular grid of where everything was spaced in the universe, and then we left it, you're absolutely right that the gravitational forces would balance. However, that's not the situation that we have. Things are, or at least we think, distributed much more randomly. So there are parts of the universe where there's more matter, and parts of the universe where there's less matter. So what you would get in those parts of the universe where there's a bit more matter, that it just eventually sucks in everything from its kind of local region, that all of that matter collapses together, and you get a big void. So you get little clumps of matter, and then the big voids in between them. So that's what I mean by the local. In a patch of universe, things would collapse.
Does it matter if the universe is finite or infinite? I'm thinking an image where perhaps you've got a stretchy net with coins or some lumps at the junction of the net, and if you stretch that out on a flat surface, it's going to contract because the elastic between them is going to pull them all back. But if it's finite, so you stretch it over a ball, then it's not going to move, is it? Because in every direction there will be the elastic pulling the lumps of mass
in all directions. So if you stretch it over a ball, it's not going to contract. It's just going to stay there in equilibrium.
Yes, no, you're like, these are all really good questions. Thank you. Yeah, no, you're exactly right. It does matter if space is finite or not. And it matters if space has what we call like an intrinsic curvature. So really, yeah, is it ball-like? Is it like a sheet? Or is it the third alternative is it's kind of super wibbly, like a lettuce leaf or something like that. And all of those different things make different predictions for exactly as you said, how you expect gravity to then these forces to balance or not balance. Your example with the net stretched over the ball is a good one. Yeah.
So sorry to carry on, but in all cases, would you expect the universe to contract under gravity, or are there certain conditions when you wouldn't?
No, so there are situations where that curvature, so is the universe better described like a sheet or a ball or a lettuce leaf, could in itself counteract the gravity pulling things together. However, we know from other kinds of observations that the universe really is pretty close anyway to being a flat sheet, that there isn't any of this kind of curvature, this extra structure there to counterbalance the gravitational forces. But that could have been a possibility. The theories allow it, and it's only with observations that we've ruled that out.
Along the same lines that you said that matter is clumpy, is the dark energy also clumpy, and how does that impact your assumptions of measuring the constant?
Yeah, no, so that is a question that we don't know the answer to yet. As far as we can tell from the data that we've got, the universe, the expansion of the universe is accelerating in the same way everywhere we can see. But you know, the data is only as good as our measurements. In the moment, Euclid is going to do a much better job of doing that. So I think I said that we've got about 800 of these supernova observations at the moment. Euclid's going to bring us many more than that. So then we can start to ask questions about is that accelerated expansion happening in the same way at all points in space, or is it actually clumpy, or is there more of it in some patches and less of it in others? So that's a question that we'd really like to be able to answer. If the answer turns out to be that it is this cosmological constant in the Einstein equations, then it would be absolutely the same everywhere and no clumpiness. But that's something we need to go and test.
I'm trying to understand the expansion of the universe. Do you mean by that the objects of matter move apart from each other, or is the space-time increasing, moving the objects away from each other?
Yeah, so it's really the space-time expanding. So if you think of things living on our expanding sheet or our stretchy elastic net, it's that net that is stretching and moving apart, and the matter objects are just sort of carried on that expansion of the space-time. I was going to say something else and I've forgotten. Yeah, no, does that answer your question?
Whether the dark energy causes the objects moving at accelerating pace, or whether the dark energy is causing expansion of space itself.
Sorry, I think I missed the beginning of your question. Sorry, could you just repeat it?
Okay, just to expand the question, does the dark energy cause objects moving apart, in other words, causing expansion of objects in the universe, or is dark energy causing expansion of space?
Right, yeah, so it's causing the expansion of space, but it's a very weak effect. So basically any other force will win over this effect. So it's not the case that we are expanding, because all of the electric forces that hold us together win easily over this tiny effect of space-time expanding. The same is true for the solar system and for the galaxy. The gravitational force holding them together wins over this tiny background effect of the space expanding. But it really is the space-time that's expanding and carrying things along on top of that.
Any more questions? Let's take one more.
I'm just wondering how, during the early inflationary period of the universe, what sort of cosmological constant did that require in comparison to that derived from quantum mechanics?
Yeah, very good. So yes, you could. So inflation is another period of accelerated expansion. The one thing we know about that is that it happened at very early times, so it's high energy, and that it had to have ended. So you can't explain inflation with a pure cosmological constant. Otherwise, you'd just have inflation forever, and we wouldn't be here. But it could be something like a cosmological constant. And then the scale of that can vary. So again, the answer to so many questions in cosmology is that we don't know. We don't know the scale of inflation. We know it has to be higher than the particle physics scales that we can study in the lab or at the LHC. But it could be just above that, or it could be way above that, up at like quantum gravity scales. So our cosmological constant to explain dark energy, maybe hang on, let me skip back to this slide. So this is the value of the energy of the density in our cosmological constant today. Inflation has to be somewhere up here, so it has to be at some point during at the point where the universe was dominated by radiation. That's the red line here that I didn't really talk about. So initially the universe is dominated by radiation, that cools, and then the matter takes over, and now we live at this time where the cosmological constant is dominating. So it could be just before radiation starts to dominate, or it could be way before. But you're talking about, what's that, like a factor of 10, 15 orders of magnitude at least, and it could be even bigger than that.
Well, thank you very much, Claire. As you can tell from the questions. Oh, we've got some on the anything online? Any other questions online? No. Well, I think you can tell from the questions that people have been fascinated by the talk, and it's been great. I'm going to ask one last one as the president's prerogative here. How certain are we that the standard candles don't evolve slightly? I mean, we know that the metallicity evolves and increases through the time. How certain are we that there's not some subtle effect which changes the magnitude of the supernovae?
Yeah, another excellent question. So in fact, we know that they're not perfect standard candles. The term that people often use now is that they are standardizable candles, because there is some variation in how bright they are, but that it seems to correlate with things like what we can infer from the metallicity, or exactly the duration, how quickly the supernova fades afterwards. So if you can make all of those measurements, then you can there's some variation, but we think we understand how to fit them to a sort of one size to a standard template to still be able to infer the distance. But going back to the question that somebody else asked earlier, that's one of the things that people are looking at. Do we really understand that well enough? And is this maybe one of the sources of the Hubble tension that people have been talking about, again, that we don't understand? So yeah, something that you have to do quite carefully and continually check, really, are you doing that properly or not? Do we understand enough about how supernova behave to be able to do that well enough?
Well, Claire, thank you very much. It's been absolutely fascinating. I'm glad it was only a meeting, that our last speaker got bitten by a dog and couldn't drive, which is, a very, very extreme way of not coming to see us. So I'm glad it was a work meeting that keeps you away. So thank you very much again. And I'm sure we've all really enjoyed it.
Thank you very much for having me.